So just when you read the assignment, you will see that I'm trying to reiterate some of this information to you, that the rules will be expression, term, and primary, and we continue on that expression starts with the term and ends with the term. Primary, the term begins with the primary, ends with the primary, and we're going to be implementing all of this. And so let's take a look at the code, right? But again, the challenge is that the grammar is a formal description of rules. It's not a programming language. It's it's very suggestive to the type of logic that we need to implement. However, it doesn't tell us how exactly in our programming language we're going to implement these rules. So the good news is that in the demo project I already put them together, so you don't have to. You just do your part to understand what this does. All right. So let me see. Let's go back all the way back to the start, and start is invoked by the main method, right? And so all that this start rule does is basically says after talking stream, let's just start at the beginning of the talking stream. It says, give me the result of this expression rule, right? So it's basically coming in here and says, well, you know what? If everything is okay, I should get back this result, which simply is this root node, right? This root node that I want to get. I don't call it a root over here. I could have called this a root node, but basically I want a single entry point into my arithmetic expression set of rules, okay? And this is a single entry point into it. So let's examine what happens over here in the expression rule. So expression rule, so basically start rule is somewhat convoluted because it does some extra things, but basically the word start here suggests to the suggests to the rest of the application. So that's where you need to get started with this interpretation of input, right? But then expression rule is actually our own top level set of rules, and let's see what happens. So first I say, if token stream is already at the end, that means nothing to do, and I will construct the node, which basically takes its type as end. And so the caller can examine the type of node that I return. It's not an offense. It's just basically I will return the node, right? One of these guys right here, right? So one of the nodes, I will just simply construct a separate node like this, and its type, right? And inside of it, its type will be set to something like end. And whoever gets this node, the caller, can take a look at the fact that this signals the end and say, okay, we understand that it was unsuccessful attempt to reach for more input, and so that's fine. Right? So it's the first check that I do. The next thing is that, as promised, according to the grammar rules, first thing that I want to check is this a term, right? And for this I say, okay, sure, let's call another method that says term rule, right? So if in grammar, if in this official grammar I just say expression, term, and primary, in my code I actually would like to give recognition to these methods as expression rule, term rule, and of course the primary rule, right? So we're gonna go back down here and take a look at the primary rule, actually the term rule, right? The term rule, and right now, because nothing else is implemented, multiplication and division would be actually the grammar for multiplication and division would be implemented at this level of our grammar. But right now I simply say, well, you know what, the term is not very sophisticated. All it does is just basically returns the result of the primary rule, right? So in my world, I do not implement multiplication, I do not implement division, I do not implement the remainder operator. All I do is that I will return a successful term only if it's a primary. So that's why, again, for whatever technical reason, I just check for the ending of the token stream just to be safe, because apparently at this point I am going to be reporting an error that it's an unexpected end of input if this rule didn't work. Otherwise, I just delegate the work to primary. And so here's the primary. So let's take a look at the primary. Again, the primary says someone wants to check for primary, but we're so far, we essentially entangled ourselves in these grammar rules so far that at this point there should be some input. Primary will not agree with returning an okay result unless there is a real primary available, such as a number. So if it's all of a sudden end of input stream, we're going to say, well, you know what? It's an error. This is unexpected end of input. We were not expecting it. Okay, so then I say, is this thing a number, right? Again, at the primary rule, if you check back with my primary rule, the first thing my responsibility is just basically say, is this a number? Now, in our talking string, fortunately, right, in our talking string, which is our object here, we have a check whether the current token is a number, and if it is a number, I immediately say, well, you know what? Very good. This rule should succeed. And what I do, I construct the node, right? One of these guys right here, right? One of these nodes that I construct, okay? And I say, well, you know what? Let's populate it with the type number so that the rest of the application will know that primary just return something that says the number. And of course, the value of this token will simply be a string which we get, right? So although I would be, when we run this application and we try to, right now we're printing everything, it prints the numbers, but internally it stores the strings. Again, for the sake of simplicity, I didn't want to, on the spot right here, deal with conversion from string to a number. To what I want to demonstrate right now, I'm very successful by basically just keeping track of my strings and not immediately proceed to convert them to numbers, which I would otherwise consider if I wasn't concerned to just keeping this demo code to as small as possible in size, right? So, all right. So we match the number. We manufacture the node of the tree, which will encapsulate the number, right? So it's going to be one of these guys, 1 or 2 over here, right? Which will be eventually added to the tree, right? And so then I immediately say next, right? I immediately say, well, you know what? We just consumed this string out of the token stream. So we just consume one token, and to signify that, we just basically tell the token stream, okay, we're ready to move on. There's nothing else to wait for. Looking at the current token, we need to proceed to the next one, and the rest of the application will be dealing with that next one. And this was called a primary, and I simply returned this AST node from the primary rule. And so therefore, in my world, in my interpretation of these rules, the primary rule returns a token that encapsulates this number. Rather, returns a node, right? Returns AST node that it just has constructed as new AST node, which takes number as the type and which stores the value as the value of the current number, but in the form of a string. So this is how these rules look like. If this wasn't a number, for example, if I run this again, right? And instead of providing a number like 1 over here, right? So 1 is basically just 1. There is no tree rather than the top level primary node, which was understood as 1. But if I use a parentheses, right, what happens if I do something like this? If I enclose my number in parentheses, which is in arithmetic a legal syntax, right? So I should be able to deal with that, and the result is exactly the same. Why? And the answer is, let me just quit this for a second so that we can just go back to the code. So first of all, we check whether the current token is a number, but it's not. Instead, I say, okay, it was not a number. Is this a string that looks like an opening parentheses, right? So, if it is an opening parentheses, then immediately, and this is the way to consume tokens, right? So, the parentheses is just the signal to the progression of our grammar rules. We don't want to store parentheses in our token, in our nodes or tree or anywhere else. We basically say, well, you know what? It's just some kind of sub-expression that we want to deal with, and we immediately proceed to the next token. Then we say, is this the end, right? So somewhere as we say next, part of our responsibility is to check whether the ending was reached. For instance, if we have an opening parentheses and we're already looking at the end of input, it's a syntax error, right? So over here, the error that I'm trying to report to the user is basically, what I'm trying to tell them. What I'm trying to tell them is that this is a bad grouping syntax and show the opening parentheses. Hopefully that's going to help them, right? So my choice is that from every grammar rule, I either return a token that contains something good, such as plus, minus, number. In the future, it could be a variable, the node in the tree that represents an actual variable such as XYZ or so forth. Or I can construct my node that indicates the type of the node as an error. And whoever calls the rule is supposed to check the thing that I returned back, whether it contains an error or not. So let's verify this, by the way, right? The closest that we can get is to this type of thing at the top level, at the expression level, right? So at this level, when we check for the term, right? So we say, first we check for the end, then we say, is this a term rule, which in our case succeeds or not? But the first thing that happens in this expression rule at the top, right? It happens here, right at the top of our rules, is that it says then, let me get this node from the term rule, right, which calls the primary rule, and immediately check whether it's an error. Well, guess what? If it's an error, I immediately return from this expression rule, and then the start rule over here, the start rule will say, oh, if the result of this entire thing just happens to be this error node, which was passed over and over and over from any level of method calls which were taking place, right? So it basically says, okay, we just immediately print the value, which is the error message, the way I populate this error AST node, and we just immediately return with false all the way back to the main method, and apparently, it's not a success. All right, so that basically can tell you what's happening at the level of these rules, which basically can call one another, and they do call. But expression rule, if you compare this expression rule to the set of these grammar rules that we have, and I can display them on side by side, right? My implementation of the expression rule anticipates there could be like number plus something else. And that something else is just another expression. It can be something parenthesized. It can be number one. It can be, number one enclosed in parentheses, or whatever else it is legal that it can contain, right? So I already, in my own version of interpret or implementation of this expression, I already say that when I evaluate my expression and I want to determine whether it's a term or not, I name it a left-hand side, right? Anticipating that maybe there could be the right-hand side, right? So whatever the first result of my check for the term is, I name it left, right? It may be just one single number, like 1, 2, 3, and that's all. But I anticipate that maybe, just maybe, there will be plus or minus. So therefore, this guy here, I will call it a left-hand side, and I simply name this node to be a left. So that's my choice for variable names right here. Okay, so then I say at the level of my expression, if the ending of it is reached, then everything is fine, and this node is returned as the result, which happens when you enter a single number without any operators. Next thing is that I want to implement this recursion, and this recursion simply is this. If the next token is plus, right? It really is a plus or a minus, all right? So I want to capture both situation with plus or minus. I simply check. Then I say, well, you know what? This node I will call the fork node, right? So you see what I'm trying to picture in this, as I was writing this implementation, basically the idea is this. This node is constructed named left, okay? Another node is constructed as fork, right? And finally, I'm just anticipating that the other one will be the right one, right? So in case if it's a plus or minus in my world, of course I will be setting it up like this, right? So the fork will contain left-hand side and the right-hand side. However, this thing right here, right? This thing over here on the side, this part does not exist, because what I do, I begin with the left first, right? So I just interpret left, and then check whether there's a plus or minus. If there is, I know, okay, it can be anything else. I want to create a fork right away, right? So I don't know what kind of fork is going to be, right? But immediately I know that I will have the left, the right in the future, and now I'm constructing the fork node, okay? So I do this basically unconditionally, right? I'm just saying, okay, if I am dealing with plus or minus, and I can check my token string for that, I immediately construct the fork node, which will be able to, or it could be also called a branch, right? Which has left and right. So I'm constructing this fork, and then I am populating the type of this as basically the character which is plus or minus, right? According to the grammar rules say that at the level of expression, and I am at the level of expression right here, right? This is purely an expression rule that I'm trying to implement and deal with. My grammar rules say that, okay, it could be number or number followed by plus and something else, right? Or minus and something else. So I just unconditionally, because I already checked for plus or minus, I just say, well, you know what? I'll populate my node type as the character plus or minus, which very successfully converts itself to an integer, which in itself gets stored as the type of the node. Because remember, the node class, if you remember what it is, the node class has the type as the first data attribute, and in my case I populate it with plus or minus, which is a character, but it gets successfully converted to an integer and gets stored as the type of the node inside the node object. Okay, so that happens, and so now what I say is that let me see, right? So we're dealing with a case where there is a plus or minus situation. But look, I just told you that I don't want to stop. I don't want to stop doing just like one. Where did I have it? Somewhere here in this demo. Yeah, right here, right? I don't want to stop doing what I'm doing simply by detecting one plus or one minus. I need to keep going because it could be like, you know, thing minus another thing plus another thing minus another thing, and pluses and minuses can be continuously be part of my talking string. So that's why this plus or minus is done in a loop. I say until there will be no more pluses or minuses. I will just keep doing this. We'll be creating the fork thing, and we'll be populating the left-hand side and right-hand side, okay? So anyway, as soon as I constructed the fork node, I say, let's move to the next token, and just to see what's going on there. If it's an AND, clearly, I say that fork is a binary operator. What it's going to print, it says error. Plus or minus is a binary operator. This is what the user will see, and I will just return this again, the error node, because I can detect this as a syntax error as soon as I proceed to the next token, right? Otherwise, I immediately make this decision that now that I know that there's something else, now I can say that fork will have the left node set, right? So the fork will contain the actual left node, which was already done at the top, right? Before we even entered into this loop, the first thing was that the left node was constructed as a result of successful term. Okay, and so that is already in place. Now we have the plus or minus fork, and so immediately at this point I say that the left hand side for the fork is going to be by my left node. So this thing right here, and let me just make it clear again, right? So far the plan is to be able to construct the left, right, the right, and the fork, and so far where I am right now is that I have already constructed the left, right? I have already constructed the left, and I have already constructed the fork, and now I'm actually making this connection, right? I'm already saying that fork left hand side should be pointing to the left. So I have this part constructed, although the right hand node doesn't even exist yet. Moving on, right? So naturally the right hand side node is also another term, right? So it's just another term. So I call the term, and anticipating then, there's another interesting aspect of it, is that once this finished, right? So once this is all finished and this is all connected like this, and I'm ready to return from whatever I am doing, I actually would like to make sure that this entire thing is going to be pointed by the left node reference, right? So I'd like to use left as this. And so that's why as soon as I specify that my fork left hand side points to the left node, I reset my left to be the fork. Okay, and I basically say whatever happens beyond this point, you can recycle my left as being pointing to the entire tree, and this is how it's done, right? So then the term, and of course if the term doesn't fail, then the right hand node is set to right, and we proceed to another plus or minus. If it happens, everything is happening in a loop. Okay, and we are assembling these nodes, connecting left and right, and keeping track of everything through this little left reference that points to the top level of our tree, right? So constantly points to the top level of our tree. And it's interesting that even before we proceeded as far as plus or minus, which causes us to create the fork node, right? Before then, the only thing that we have is the left node. The left node is constructed first, and we say, well, we always expect this to be there. In case if there's a plus or minus, we will construct the fork, make this connection, and make left point to the fork, basically point to the fork, so that it can be reused in the future. And then this succeeds, and we make this connection, and we keep building, right? So if there's another plus or minus happens to be here, then again the fork, another fork node is constructed, immediately connected with the left, which essentially is connected with our prior fork, and then the right hand side evaluated, and the right node is constructed, and the left node is repointed to this new fork, top level fork, right? So this left node basically constantly keeps track of the root of what we were able to construct so far by simply looking at terms and pluses and minuses, right? So this could construct us quite a bit of nodes and everything, just simply looping through this loop inside the expression rule, right? But eventually it's going to return the left as a reference to the top level fork, and from that point on we can construct it, we can use it in whatever else a part of our grammar we use to then work with the tree. So you can see that it's somewhat tedious the way I construct these nodes and make connections between them. So the outcome is some sort of a tree constructed with respectfully, of course, right, to the grammar rule and parentheses, right? So it's all, I know this is not absolutely trivial type of code. You have to you have to follow what I'm trying to tell you, and you need to look at the code. And if you have some challenges with it, maybe you need to bring back your question. And by the way, any questions right now? I know it's been a long day already, so let's actually finish this presentation because I'm trying to record it.